Welcome to the course on an introduction to information theory. So today we are going to talk about universal source compression algorithms. The source compression algorithm that we have studied so far requires you to have knowledge about the source distribution a priori. Now, many times we do not have that information with us, right? So how do you do source compression? So that's our topic of discussion today. So we will, under this we'll talk about Lempel-Ziv algorithm. In this class we will talk about Lempel-Ziv 77 algorithm, and in the next lecture we'll talk about Lempel-Ziv Welsh algorithm. So we'll talk about the encoding and decoding of Lempel-Ziv 77 algorithm in this particular lecture. So as I mentioned, the source compression algorithm that we have talked about so far, take Huffman coding, Stungstal coding, Shannon-Fano codes, they all require a priori the knowledge about the source distribution. If you do not have that knowledge about the source distribution, you cannot do optimally the source compression. So in many times we do not have that information available with us. So what if you do not have that information available to us? What should you do? One possible thing is we could create a statistical model. So you have some initial training phase, you try to guess the probability of these various symbols which are being emitted by this source, and you create a statistical model. Other techniques could be using source compression algorithm that do not require this a priori knowledge about the source distribution. And today we are going to talk about such source compression algorithms that do not require a priori information about the source distribution. So universal source compression algorithms are the source coding algorithms that do not require any knowledge about the statistical model about the source. And they are very efficient. We are not going to talk about in this class about the optimality of these algorithms, but asymptotically they are also optimal. Now these algorithms are widely used in practice. For example, variant of this LZ77 algorithm is used in this compression software gzip and PNG, whereas zip, compress, TIFF, they uses a variant of Lempel-Ziv Welsh algorithm. So we will talk about these two Lempel-Ziv algorithms in this lecture and the next lecture. So let us first describe the notations that we are going to use for this particular lecture. So I'm going to denote my source alphabet by 0, 1, 2, Q minus 1, where Q is the cardinality of my source alphabet. The source output is denoted by small w, and K denotes the output at time K. So if I write source over all possible times, then I will use this notation WK, where K goes from minus infinity to infinity. Now the string that I want to compress is a block of length n, which I denote by this capital W, and I use these indices 1 to n to denote it's a block from 1 to n. So this can be written as string which goes from k equal to 1 to n. I use this notation Wij to denote a substring starting at k equal to I and going up to k equal to j. And I can write this string from k going from I to j as a string going from I to j minus 1 concatenated with another output at time j. So wij minus 1 can be considered as a prefix, and wj is a what we call an innovation symbol that makes wij different from wij minus 1. The string of code words we will denote by C. So C of L, where L goes from 0 to L, basically L set of L code words, that those will be denoted by C of L. So this Lempel-Ziv 77 algorithm was given by Jacob Ziff and Abraham Lempel in 1977, and this is also known as sliding window version of Lempel-Ziv algorithm, and it's a dictionary based source compression algorithm. We'll talk about that. So we are given a string of n bits that we want to compress, and set of code words is given by C of L, and these code words uniquely determine the substrings or this set of code words complete describe the string that we are encoding. Now each code word, so as I said, this block of n bits is described by code words. CL goes from 0 to L. Now each of these code words CL uniquely determine a substring YL of this block of n bits. The length of this substring is variable, and our objective is to minimize the number of bits required to represent these string. So we would like to minimize the number of bits required to represent our set of code words. So as I said, this is a dictionary based source compression algorithm, and we will talk about how do we create a dictionary. So a substring in the source is replaced by a code word that uniquely identifies that substring in the dictionary. So we are going to represent this string. So you can think of it as this string that we want to encode can be partitioned into smaller substrings, and corresponding to each of these substrings there is a code word. Now how do we partition it into these substrings depends on what is there in our dictionary, and we will talk about that. Each code word except the initial code word, which I call as zeroth code word, each code word except the zeroth code word is concatenation of two parameters. One is the length of the match of the substring, which I denote by capital L, and ML, which denotes the location where the match has occurred. So as I said, it's a dictionary based encoding. So the string of bits are there in the dictionary. So whenever a new string comes in, or we are searching for the largest newer string which is already there in the dictionary. So we are interested in finding out the length of the string that is matched to a string which is already there in the dictionary, and we are also interested in finding where in the location of the dictionary this match is occurring. So we are interested in two things when we specify code words except the zeroth code word, and these two things, as I said, are these parameter L and M. What is this parameter L? L is the length of the text from the given parse which is there in the dictionary, which got matched, and this M is related to location in the dictionary where the match has happened. So our set of code words is as follows. Initially, the set of code words is essentially a set of bits that we are encoding, like so we have a dictionary of window length NW, okay, that is much smaller than the block of data that we are trying to encode. So initially we will send the first NW bits, but that's our initial dictionary. Then subsequently what we are trying to do is, we are trying to find the largest match of the string. So starting from location NW plus 1, we are looking at largest string which gets mapped to a string already present in the dictionary. And we are interested in knowing how long is that string matched, and we are also interested in knowing the location of the match. And what we are going to do is, we are going to code these two parameter L and M, and this will be our code word. As I mentioned, this is a sliding window kind of version of Lempel-Ziv algorithm. So I have a window of size NW, and typically this is taken as power of 2. So in this scheme, both encoder and decoder, they maintain a dictionary containing most recent NW bits. So both encoder and decoder are maintaining a dictionary of most recent received NW encoded source bit symbols. When encoding a substring starting from a source symbol WK, the dictionary contains source symbols from WK minus 1, K minus NW to K minus 1. So if you have a string of bits, this is a string of bits, and let's say I am looking at kth location. So what you are going to see is, from location K minus 1 to, so this location K minus NW to K minus 1, these bits are there in your dictionary. So this dictionary is of size NW, okay, and this is in the dictionary, and you are looking at the kth bit, which is WK. Now how do you encode this string coming out of WK? What you do is, so initially the first NW symbols of your sequence that you want to encode, those are initially sent to the decoder. So initially the decoder is initialized with the first NW symbols of the string that you are trying to encode. So the first code word C0 is nothing but initial NW contents of the dictionary. Next, second code word C1 is found by searching for the largest substring Y1 beginning at location NW plus 1 such that Y1 starts in the dictionary and end L1 times later. So what we are doing is, so initially as I said 1 to NW, this is my initial NW symbols, they are in the dictionary. Now I look at the next symbol, which is NW plus 1. Now what I am going to do is, I am going to look at a string, largest string starting at location NW1, which is already there in the dictionary. So my dictionary contains, as I said, my dictionary contains symbols from location from time K minus NW to K minus 1. So it has some symbols of length NW in the dictionary. Now at location NW plus 1, I am trying to look at what is the largest string, which is already there in the dictionary. So this match, so let's say this is 0, 1, 0, 1. So I look at in the dictionary where my 0, 1, 0, 1 is there. So I look at first in the dictionary where my 0 is. So there might be multiple places where 0 is. Then I look at, okay, 0, 1, which are the locations where 0, 1 is there? Maybe there are few of them. Then I look at 0, 1, 0. Is there a match with 0, 1, 0? Then I look at 0, 1, 0, 1. So I am trying to find the largest match which is already there in the dictionary. And please note, this match has to start inside the dictionary. So that's what I meant. I am searching for the largest substring beginning at time nw plus 1 such that this substring starts in the dictionary and end L1 times later. And I also need to find out where in the dictionary this match is starting, and that is given by this P. So the index of the dictionary symbol where copy of Y1 begins is denoted by P, and M is given by NW minus P. So let's say my NW is 16 and this match happened at third location. Okay, so then M1 would be 16 minus 3, which is 13. Now there might be multiple places where I have match of the largest string, right? So which value of M should I choose? I should choose the smallest value of M. The reason being, if I am using variable length coding to describe these M, the smaller the M, I will require lesser number of bits. However, if I am using fixed number of bits to represent M, then it does not matter what choice of M I use. So once I have found out the largest map of the string Y1 inside the dictionary, what I am going to do is, my code word C1 is nothing but this pair of length of match and this M1. So this will give me the code word C1. Next, I am going to update my dictionary. Now how I am going to update my dictionary? I am going to update my dictionary by deleting the L1 oldest entries from the dictionary and adding this new L1 bits. So look at this. So I had these NW bits in my dictionary, right? Now I looked for the maximum match. So this string Y1, so there was match of length L1. So what I am going to do is, I am going to remove these L1 oldest bits from the dictionary, and my new dictionary is now this. So note, my dictionary size remains same, it's just sliding. Okay, my dictionary size is still NW. I deleted this old L1 bits symbols from the dictionary. Instead I added this new L1 symbols corresponding to the substring Y1, and I repeat this process. Next I will look at the largest string starting from this location, which is already there in my this dictionary, and let's say that substring comes out to be Y2. Okay, then I'll again find out what is the length of the match, and I'll find out the location of the match, which is related to M2. And then I will add this L2 bits to my dictionary and remove old L2 bits. I'll remove this old L2 bits. So my new dictionary now will be this. So this process of sliding the dictionary and finding the largest substring which is already there in dictionary, this process will continue until I come to the end of the block which I want to encode. So that's what I said. After I determine this code word, the third code word is found by finding the largest substring Y2 beginning at this location NW plus L1 plus 1 such that Y2 starts in the dictionary and ends L2 time units later. And I also need to calculate the location where the match has happened. That index is given by P, and P and M are related by this relationship. Again, I will update my dictionary. I'll add these substring y2, which is of length L2, and I will remove the oldest L2 entries. So this process is going to be repeated until the full sequence has been encoded. So let us take an example to illustrate what we have said so far. So we have a sequence of bits which I denote, so binary bits which I want to encode using Lempel-Ziv 77 algorithm, and it is given that the dictionary size is 8. Okay, so then what is the first step? Of the initial code word is nothing but first NW symbol. So this is, so you can see at L equal to 0, I look at the first 8 symbols, 1, 2, 3, 4, 5, 6, 7, 8. So this is my initial contents of the dictionary, which I am writing it here. So initial code word, the 0th code word is nothing but these NW bits. So the receiver has now this dictionary. Now what is the next step? The next step is, starting from this location, I need to find the largest match in the dictionary. So let's look at, is 0 there? Is 0 there in dictionary? Dictionary has this. Yes, 0 is here, euro is here, euro is here, 0 is here, euro is here. What about 0, 0? Is 0, 0 there in the dictionary? The answer to this is yes. Look here, this is 0, 0. Starting from this location is 0, 0. Of course, at this location 0, 0 match is not there, but at this location we have 0, 0. What about 0, 0, 1? Do we have a match of 0, 0, 1? So where are the two places we had match? We had match at this location, but this is 0, 0, 1. So we don't have a match of 0, 0, 0. What about this? Do we have a match of 0, 0, 0? The answer is no, because this is 0, 0, 1. So the largest substring that is matched with the symbols in the dictionary is 0, 0. So the substring y1 is 0, 0. So that's what I'm writing. Okay. Now what is the length of the match? That's 2. Now which are the locations where the match has happened? So if I write this as 1, 2, 3, 4, 5, 6, 7, 8, the match has happened at p equal to 1 and at p equal to 6. So correspondingly m is nw minus p, which is 7, and in this case it is 2. So since this is smaller, I am taking this m. So that is my m. So then my code word consists of this length of 2 and the location, which is denoted by this 2. How do I encode this L and M? I'll come to that later. I am right now just parsing my sequence into the match, length of the match and the location of the match. Now, so I have found a string y1 which is 0, 0, which is matching with whatever is there in my dictionary at location, which is given by m equal to 2. So next step is I am going to add these two symbols into my dictionary, and I am going to remove the oldest 2 terms. So my new dictionary is given by this. So that's what I have here. You look here, my dictionary is 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. So I added this string y1, which was of length 2, and removed the two oldest entries from the dictionary. So my new dictionary is now this. Okay, so my new dictionary is this. This is my new dictionary, contents of my new dictionary. Now again follow the same procedure. Start from this location 0. Is there a match of 0? Yes, there is. Here there is a match, 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 here there is a match. Right? What about 0, 0? Now here there is no match of 0, 0, but here there is a match of 0. Here there is no match of 0, 0, so I just remove this. Here there is a match of 0, 0, and here also there is a match of 0, 0, because this 0 is followed by this 0. So the match has to start within the dictionary, but it can go beyond. Okay, so if you look at, so there is a match of 0, 0. What about 0, 0, 0? Now at this location this is 0, 0, 1, so this is not a match. But what about this? At this location it is 0, 0, 0. Similarly at this location this is 0, 0, 0. So there is a match of 0, 0, 0. What about 0, 0, 1? Look here, this is 0, 0, 0, 0. So that's not a match. What about here at this location? This is 0, 0, 0, 0. So clearly there is no match of 0, 0, 0, 0, 1. So the largest match is 0, 0, 0. So this substring y2 is 0, 0, 0. So then the largest map is this 0, 0, 0. What is the length of this match? That is 3, because the string of length 3 is getting mapped. And what is the location? So this match happens at this location, which corresponds to p equal to 7, or the match happens at this location, which happens to be p equal to 8. So m is either 1 or m is equal to 0. So as I said, we take the smallest m, so we take m to be 0. So corresponding to the string y2, we have a string of length 3 and location m given by 0. Now the next step is we are going to add these string y2 to the dictionary, and we are going to remove the 3 oldest entries. So our new dictionary is this, and that's what I have written here. You can check, it's 0010, 0010, 0000, 0000. So the new dictionary is given by this. Again we follow the same procedure. So we look at the first bit 1. Is there a match of 1 here? Do you see a match of 1 here in this dictionary? Yes, there is. That's this. What about 1, 1? Is there a match of 1, 1? The answer is no. So there is only a match of 1 here. So then what I am going to do is, the substring which gets matched is 1. It is of length 1, and this corresponds to p equal to 3. So it corresponds to m equal to 5. So this is m equal to 5. So the code word corresponds to match string 1 is 1 and 5. Okay. So we further continue this process, and what we are going to do next is we are going to now include this 1 into our dictionary. Okay, we are going to include this 1 and delete this 1. So what we are left is this. So we deleted this thing and added this 1. So the new dictionary is now given by this, which is this 0100 0001. Now we again start with this symbol 1. There is a match here. There is a match here. Now 1 0. 1 0, there is a match here, but here there is no match. So there is a match only here. What about 1 0 1? There is no match of 1 0 1. You can see this is 1 0 0. So the largest match that we are getting is corresponding to 1 0. So this new string y4 is then 1 0. So that's 1 0, length 2, and the match is occurring at this location, which corresponds to p equal to 2. So then m is equal to 6. So m is 6. That's this. We'll add these two symbols to my dictionary and remove these two symbols. So my new dictionary now is this one. This is my new dictionary. So note that the dictionary is sliding across this sequence that we are trying to encode. So this is my new dictionary. You can see 0 0 0 0 0 1 1 0 0 0 0 0 0 1 1 0. That's my new dictionary. Now we again follow the same procedure. Let's see the match. 1. Let's just clean up a little bit. So this is my new dictionary, right? Is 1 getting matched? There's a match of 1 here. There's a match of 1 here. What about 1 1? 1 1 is getting matched here, but there is no match of 1 1 at this location. What about 1 1 0? We can see there's a match of 1 1 0 here. What about 1 1 0 1? Again, there's a match of 1 1 0 1. What about 1 1 0 1 1? Again, there's a match. And what about this? 1 1 0 1 1 0. 1 1 0 1 1 0. So please note the match has to start inside the dictionary, but it can go beyond. What about this? 1 1 0 1 1 0 0 0. 1 1 0 1 1 0 0 0 is not there. So the maximum match that we are getting here is corresponding to this 1 1 0 1 1 0. So the new string y5 is basically 1 1 0 1 1 0, and that's this. And what is the length of this string? The length of this string is 6. That's this. And what is the p corresponding to the match? The match happens at this location, which is 1 2 3 4 5 6. So p equal to 6. Then m corresponds to nw, which is 8 minus p. So 8 minus 6 is 2. So this is my m. So corresponding to this string, my code word is 6 and 2. Now I need to add these 6 symbols to my dictionary, and I'll remove the oldest 6. So I'll remove this, 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 this. So my new dictionary is now this. This is my new dictionary. And you can check my dictionary 1011 0110 1011 0110. Okay, I again look at for the maximum match. Let's just clean up a little bit. Okay, so I look for the maximum match. 0. Is there a match of 0? Yes, that's this, that's this, that's this. What about 0 0? There's no match of 0 0 here. So I just removed because this is 0 1. There's no match of 0 0 here also. But there is a match of 0 0, that's at this. So the maximum string that gets matched is 0 0. It's of length 2, and the match happens at p equal to 8. So nw minus p, m comes out to be 0. So note that now we have encoded this whole string. So this list of code word is given by this. So this is a code word corresponding to the string. So what we need to send to the receiver is now, we need to send some representation of these numbers, because the decoder has to understand that length is 2 and m is 2, length is 3 and m is 0. Okay, so we need to communicate to the receiver these li and mi's, this length and the location where the match is happening. So how do we do that? So we will show that in the next slide. So we are going to do what we call comma-free encoding of M and L. Now of course, we would like to know, if we are using variable length codes, we would like to know where are the boundaries of L and M. So decode, if we use a comma-free code, the encoding decoder can directly identify the beginning of a new code word from the sequence of numbers that is receiving. So one such encoding scheme is given by Weiner and Ziv. So this is as follows. So if you have a positive number k, we denote its binary representation by b of k, and number of bits required to represent the binary number, which is basically given by this quantity, is we denote it by absolute value of bk. So let's say I have k equal to 4. So the binary representation b of k is 100, and this term will be equal to 3, because I need 3 bits to represent 4. Similarly, if k is 8, then b of k will be 1000, and this term will be equal to 4. Okay. Now they defined a binary sequence of k minus 1 zeros followed by 1, which they denote by u of k. So for example, u of 3 is basically 0 0 1, u of 2 is 0 1, like that. So the comma and free encoding of this length of the match of this substring, this was given by this. So comma free encoding of L is given by E hat of number of bits required to represent the binary representation of L concatenated with this binary representation of L, and this quantity is given by U of number of bits required to represent this into binary representation of this. So let's take an example. Let's see L length is 4. So according to this, then E of 4 will be E hat of, now binary representation of 4 is what? 100. So how many bits we require to represent this 4? That's 3. So this will be E hat of 3. And what is the binary representation of 4? That is 100. Okay. And how do we find out E hat of 3? That is nothing but U of, now how do we write 3? 3 is written as 1 1 1. So number of bits required to represent 3 is 2. So this will be U of 2 and binary representation of 3, which is 1 1, right? And E of 2 is nothing but 0 1. So then E of 4 is given by 0 1 1 1 1 0 0. Now note how we can identify 4 from here. So from the runs of zeros, we find out how many next bits we should look at. So here we have one run of 0. So we should look at next 2 bits. So we look at next 2 bits. that is this. So next 2 bit is 1 1, which is 3. Now I look at next 3 bits, that's a number which has been encoded. So this number is 4. You can try out other examples as well. Let's say you want E of 3. So this will be E hat. Now 3 is represented using 1 1. So this will be E hat of 2. And what is the binary representation of 3? That is 1 1. Okay. Now E hat of 2 can be written as, now what is 2? 2 is 1 0. Binary representation of 2 is 1 0. So we require 2 bits to represent 1 0. So this would be then U of 2, and 2 is 1 0. So this is nothing but 0 1 1 0. So E of 3 would be 0 1 1 0 1 1. And note, how do we find out 2 from here? So run of zeros is 1 run of 0. So we look at next 2 bits. What is the next 2 bits? That is 2. So we look at next 2 bit, and that's a number which has been encoded, which is 3. So this is how we are going to encode our information about Li, and we could use the same thing for Mi as well, but we are just right now using fixed number of bits, which we are denoting by log of NW bits. Now, how does the decoding happens? So what the decoder will do is, decoder will receive this encoded sequence, which is nothing but the initial NW bits and the encoding of L and M. So the first thing that the decoder has to do is, from the received sequence, it has to find out the values of Li and Mi's, right? So first NW bits are nothing but, those were the initial bits that were encoded, and then to determine L1, as I said, the decoder will read a sequence of zeros followed by the first one to determine the length of encoding, which is P1. Now once it's known what a P1 is, those number of bits are going to be used to represent the length of L1, and once it knows the length of L1, it will look at subsequent L1 bits to find out what was the bit that was encoded. And we just gave an example to illustrate that. Remember, we did, let's say, comma free coding of E4 was comma free coding of number of bits required to represent 4, followed by binary representation of 4, and this was given by run of 1 1. Binary representation of 3 is 1 1. So this is U of 2 followed by 1 1, and U of 2 was basically 0 1 1 1. So E4 was 0 1 1 1 1 0. So that's what I'm saying. The decoder first reads the sequence of 1. So it starts reading a sequence of 1, followed by the first one to determine the length of encoding of P1. So there's only single run of zeros. So the length of encoding of P1 is going to be 2, because U of k was 0k minus 1 1. So the length of encoding of P1 is, in this example, is 2. That's this, which is then used to determine the number of bits used to represent L1. So this, we look at next 2 bits. This will tell us number of bits used to represent L. And what is this? This is 3. So we have knowledge about that next 3 bits are used to represent L. So we look at next 3 bits, and what is that? That is 1 0 0. That is the binary representation of 4, and that's how we decode that this L is 4. right? So that's how we do it. Now, having determined L1, then since we are using fixed number of bits to represent M, so we know what are the next bits that we should look at. In our example that we have considered, our NW is 8. So that means we are using next 3 bits to represent M, right? So depending on the value of M from 0 to 7, we are using 000 to 111 to represent M. So we can find out then what is L1 and what is M1. Now once L1 and M1 are known, then we can find out the phrase Y1 from the dictionary. Why? Because Y1 was the string that was matched to what was already there in the dictionary. The length of the match was L1 and the location of the match was a function of M. So if I give you Y1 and M1, you can find out what is the string that is matched with the dictionary. So I can find out Y1. Now once I find out Y1, the next step is to append this Y1 to my dictionary and remove the old L1 entries from the dictionary. So my new dictionary will now have these Y1 string and will have the old L1 bits removed. So this Y1 will be appended to a dictionary. Next, the dictionary is updated by deleting the oldest L1 entries and appending the phrase Y1 to the dictionary. So that is my new dictionary. Now I have my dictionary. I'll again repeat this process to find out what my L2 is and what is my M2 is. Once I find out what my L2 and M2 are, I'm going to find out the string Y2 which is of length L2 from my new dictionary, and I'm going to add this string Y2 to my dictionary and remove the oldest L2 entry. So now that will be my new dictionary. Then again I'll decode what my L3 and M3 were, and then I will, from the dictionary, I'll find out the new string Y3. I'm going to add this string to my dictionary and remove the oldest L3 entry. So this procedure is repeated until the original sequence is completely reconstructed. Now since these match happened from the dictionary, I know what exactly those strings were. So let us take an example to illustrate that. Now this is the received sequence that I have received. Now I am considering the same example. So my NW is 8, which is known to the dictionary, which is known to the encoder and decoder, that the size of this sliding window dictionary is 8. And I am using comma free encoding for these LIs, and I am using fixed number of bits to denote these MIs. So log of 8 was 3, so I am using 3 bits to denote MI, and for LI I am using comma free encoding. So how do I decode this string? So let us first find out. So what does this is a set of code words I have received, right? So what does this code word consist of? This code word consists of, so first 8 bits are nothing but the initial sequence that I wanted to encode, and subsequently I will have the value of L1, M1, L2, M2 like that, right? So let us first, from this particular receive sequence, try to find out these code words corresponding to L1, M1, L2, M2. So as I said, the first, because NW is 8, so the first 8 bits are my initial sequence, 1, 2, 3, 4, 5, 6, 7, 8. So this is my initial sequence that I transmitted. Next, is encoding for Li, L1. So there's a run of single one, so I should look at next 2 bits. This is the encoding for P1, so this next 2 bits is binary number is 2. So the next 2 bits are going to be my actual value which has been encoded. And what is that? What is this next 2 bit? That is 1 0. So L1 is 2. Okay. Next, after I encode L1, I'm using next 3 bits to encode M. So what is M? M1 is 2. 0 1 0 is 2. Again, so this I have to now find L2. So there's a run of single 0. So I should look at next 2 bits. That is 2. So then these next 2 locations, the number written at next 2 bits will give me the number which has been encoded. So that is 1 1. So L2 is 3. Next 3 bits are used for M2. So M2 is 0. Okay. Now here there is 0 run of 1. So I should look at next bit. That basically says I should look at next 1 bit, and so that is going to tell me that that's 1. So here L3 is 1 and next 3 bits will give me value of M. So M3 is 5. This is a run of 1. So I should look at next 2 bits, that is 2. So the next 2 bits will give me the encoding of the number that this is 2. So L4 is 2. And next 3 bits are corresponding to M. So M4 is 6. Here I look at run of 1. So I look at next 2 bits, that's 3. So the next 3 bits will give me the value of L5, and that is 6. So L5 is 6. And the next 3 bits are used for encoding of M, and that is 2. So M5 is 2. And again here there's a run of 1. So look at next 2 bits, that is 2. So again look at next 2 bits. So L6 comes out to be 2, and the next 3 bits corresponds to M6, which is 0. So now what I have done is I have actually decoded the string into initial string and L1 M1, L2 M2, L3 M3, L4 M4, L5 M5 and L6 M6. So that's what I did. This was my L1 M1, L2 M2, L3 M3, L4 M4, L5 M5 and L6 M6, and this was my initial NW bits, right? So I have this. Now what do I need to do? Once I know these LIs, MIs, now I need to find out what is the corresponding string Y1 corresponding to this L1 M2. What is the substring Y2 corresponding to this L2 M2. So I need to find these substrings. And what is the procedure? So I start with initial dictionary, which is this. I look at a match of length 2 which starts at m equal to 2. So m equal to 2 corresponds to p equal to 6. So I look at location number 6. So what is that? 1, 2, 3, 4, 5, 6. So I look at this. So there is a match of length 2 at location index 6 because M is 2. So what is so then the match is, so starting at this location, match of 2 will be 0 0. So what I have found out is the string y1 is 0 0. Okay. Now what is the next step? The next step is I need to add the string to my initial dictionary, and I will get rid of the oldest 2 entries. So my new dictionary will be now 1 0 1 0 0 1 0 0. Right? Now I look at this. I need to find y2. So what? There's a match of length 3 and p is m is 0. So m is 0 means p equal to 8. M is 0 means p equal to 8. So I have a match here of length 3, right, and starting at this location. Now how do I find match of length 3? I only have first bit here. So clearly the match starts from this location, then the first bit here has to be 0 because the match starting at this location. Now match starting at this location, this is 0 0, so the next bit has to be 0. Right? So we have found out that the string that is matched y2 is 0 0 0. So what do we need to do is we append this new string to our dictionary and remove the 3 oldest entries. So this we continue essentially. So if you look at, initially we had these 8 bits, we found out that this was the match, and our dictionary at that time was, new dictionary was this. Similarly we found out that the next match was y2 was 0 0 0, so we got rid of the next 3 bits and this was our new dictionary. Now this process is going to be continued for the remaining. So look at this one. Here L1 is 1 and M is 5. So then P corresponds to 3. So we look at first, second, third, that's this. So we look at this location and we look at match of 1. And what's that match of 1? That is 1. So we add that 1 here and we get rid of this entry. So our new dictionary now is this. Next we look at this. So here M corresponds to 6. So that corresponds to P equal to 2. So look at this location 2, which would be, so our dictionary here was, let me clean up a little bit. So our dictionary was this. Our dictionary was this 0 1 0 0 0 0 0 1. So if you look at P equal to 2, that is this, right, and you have a match of length 2, that is 1 0. So you have a match of length 2, that is 1 0. You append this to your dictionary, so and remove the next bit. So your new dictionary is actually this. Your new dictionary is this. Now look at this one. L is 6, M is 2. So M is 2 meaning this corresponds to P is 6. So look at 6th entry, 1 2 3 4 5 6. So look at this. So we have to look at match of length 6. Now first match is 1, that's this. Second match is 1, that's this. Third match is this, so that's this. Now the fourth match here is 1, so that's this. Fifth match is this, that is this, and sixth match is 0. So this is the string that has been added. Now my new dictionary will be, and I'll get rid of the 6 bits. So I'll get rid of 1, 2, 3, 4, 5, 6. So my new dictionary is this one. Okay, this is my new dictionary. This is my new dictionary. Now here L is 2 and M is 0. M is 0 meaning P is equal to 8. So I need to find a string of length 2 matching here. So this is 0. So this has to be 0 and next match has to be 0. So this way you can see I've been able to decode this whole string. Okay, again to recap, what we did was initially we received NW bits and then we subsequently received the coding for LI and MI. So we first from the comma free encoded bits of LI and MI, we found out what those L1, M1, L2, M2, L3, M3 were. Then what we did was, since we knew L1, M1, L2, M2, we knew exactly how long is the match in the dictionary and where is the location of the match in the dictionary. So we, using the knowledge of LI, MI, we found out the substring that is matched with what was there in the dictionary. Now once we matched the substring, we added that substring to the dictionary and removed LI bits, the oldest LI bits from the dictionary. So our new dictionary was this YI appended with oldest LI bits removed. Once we have this new dictionary, then we moved out to next value of L1, LI and MI, and again we repeated the same procedure. We looked at the location where the match was and we looked at the length of the location match. From there we found out what was the string that got matched. Then we appended that string to the dictionary, removed LI bits from the old dictionary, and we progressed until we we decoded all the bits. So this is how basically you can see it's a sliding window version where the dictionary is sliding over the bits that we're transmitting. Okay, so with this we conclude our discussion on Lempel-Ziv 77 algorithm, encoding and decoding. In the next class we will talk about Lempel-Ziv Welsh algorithm. Thank you.